Thank you everyone for listening to my talk. I'm Samuel Livingstone from Statistical Science at UCL, and I want to talk to you a little bit about scalable and easy to tune MCMC. So obviously I'm talking about Markov chain Monte Carlo. Everything I'm going to talk about is within the Metropolis Hastings framework. So just a very brief revision of this algorithm. It's an iterative approach where if you've got the current point in your Markov chain is X here, you're going to draw the next point in your Markov chain according to some candidate transition kernel, which is this Q here. And the next point is going to be a proposal Y. And we'll choose the next point in my Markov chain to be either Y, which happens with this probability, or X. And the result is going to be a Markov chain which has limiting distribution pi. Right? So pi is typically a distribution we want to sample from, and we're doing this so that we can do it. And the game is to choose a Q such that your Markov chain has good properties, it mixes quickly. So I want to talk about three typical ways to choose a Q in Metropolis Hastings, so three popular proposals. And the first one is called the random walk Metropolis, and it's very simple. You just take the current point in your Markov chain and you add some zero mean symmetric noise to it. So in the Gaussian case it looks like this. And there are two tuning parameters for this method. One is this sigma squared, which is a kind of global scaling, and the other one is this capital sigma, which is a preconditioning matrix, and you typically try to get this to match the covariance matrix of your target distribution. The second proposal mechanism I want to talk about is called the Metropolis Adjusted Langevin algorithm, or MALA. And it looks quite similar to the random walk. The only difference is you've got this additional drift term. So rather than just adding some zero mean noise to the current point to generate the next proposal, you also add some kind of drift in the direction of the gradient of log pi. Right? So the idea is that you're sending your proposals uphill. And the third one I want to mention is something called HMC, Hamiltonian Monte Carlo, and it looks a bit crazy, but it's really doing something very similar to MALA, right? You're taking small steps in the direction of the gradient, and you're also adding some kind of noise. And the key point from that slide is really that the second two mechanisms I've shown you both rely on gradients, and they tend to use these gradients to design what we call informed proposals that are hopefully going to produce better sampling and a faster mixing Markov chain towards pi. So how do these methods perform in high dimensions? Well, we have various kind of nice scaling arguments as the dimension of the state space increases, and you'll often see a table like this in an MCMC talk, and it will tell you that the random walk Metropolis scales as d to the minus 1, and MALA and HMC it's a little bit different. It tends to be that all MCMC methods degrade as dimension increases, with the exception of a few specifically designed methods. But the rate of decrease is slower for MALA and HMC than for random walk Metropolis. So you might be tempted to conclude that gradient-based methods scale better to high-dimensional settings. But there's an important caveat here, which is that this is true provided they're well-tuned. These scaling arguments are based on the idea that you've chosen good tuning parameters for your algorithms. Now we want to consider the case where you may not have done that. So it's a natural question to ask, how easy is it to tune these algorithms? And to convince you that it's not that easy, I've got a quote from Radford Neal here from a paper in 2003 where he says, Hamiltonian Monte Carlo works very well provided it's tuned properly. However, choosing a step size for Hamiltonian Monte Carlo which is too large is disastrous. And it's not very difficult to show that, actually. So I've got three toy models here, just one-dimensional Gaussian, Laplace and student's T. And what I've plotted on the y-axis is the expected squared jump distance of a Markov chain, so bigger is better. And on the x-axis I've got the proposal step size. And the black line represents the random walk Metropolis. And you can see as the step size gets bigger and bigger and bigger, the expected squared jump distance gets better and better and better, and then at some point gets a bit worse and worse and worse. Whereas the same plot for MALA, it gets better and better and better and better, but then there's this kind of cliff edge drop in performance. And there's this indication that choosing a step size that is too big is going to cause a major problem with the performance of the method. And you can see that this is in some sense independent of the target distribution because it happens across 3 different targets with very different tail behaviors. So the first contribution we make is to kind of formalize this idea. So we show that this phenomenon of robustness to tuning can be characterized through the spectral gap of a Markov chain. So for a spectral gap, it's a general property of a Markov chain, and a bigger spectral gap, a larger spectral gap, tends to mean a faster mixing Markov chain. So we let the step size be fixed, and we take the scales of the target distribution to be smaller and smaller and smaller, and we study how the spectral gaps decay to 0. And we find that for the random walk metropolis, the spectral gaps decay polynomially fast as in this degree of mismatch. And whereas for the gradient-based methods, they decay exponentially fast. So this suggests that the penalty for poor tuning is more severe for Mala and HMC. So the natural question to ask is, well, can we develop a gradient-based method that is more robust? And of course the answer is yes, and that's the main contribution of our work. And we're calling it the Barker proposal, and I just want to give you a flavor in one dimension of how it works. So the headline is that it scales like Mala. You get this d to the minus third scaling with dimension, but it has the robustness properties of the random walk metropolis. The spectral gaps decay polynomially in the setting that I discussed. And the way it works is that if you've got the current point x, you draw some random Gaussian noise, xi, just like you do in the random walk. But then you choose this other random variable b, and you'll set it to be 1 or minus 1, and the probability that you choose it to be 1 depends on both xi and the gradient of log pi. And your final proposal ends up being x plus b times xi. So the variable b decides whether or not you want to flip the sign of your random noise that you're going to add to your current point. So let's just take a closer look at what's going on here. So you've got some random noise xi, and you've got a gradient of log pi at x. And if they have the same sign, then what's going to happen is that this b is more likely to be 1 than minus 1. So the most likely proposal is going to be x plus xi. So that makes sense, right? Because you're moving in the direction of the gradient. Xi and grad log pi have the same sign. However, if they have different signs, then xi would take you in the opposite direction to the gradient. And you still could go that way, but it's more likely that you're going to flip the sign and head in the direction of the gradient. And the result of this is that your proposal is skew normal. So you start with some Gaussian noise, and then you skew it in the direction of the gradient. And this is in contrast to Mala, where the proposal has the current point, and you add xi, but then you have some kind of additive drift towards the direction of the gradient. And it's this different way in which the gradient feeds into the proposal that gives us this extra robustness. So just to take a toy example, so we're more clear here, let's consider target distribution here. Current point is x, the gradient's pointing in that direction. We sample xi, which is Gaussian, and x plus c will look like that. X minus c will be over here. And because x plus xi is taking us in the direction of the gradient, then you can see the probability that b is 1 is very high. So that will be the most likely proposal. So this is a picture of what the proposal distributions are going to look like in aggregate. In more than one dimension, we flip each coordinate independently. We have some discussion of why we do it that way in the preprint. So just a quick example to give you a flavor of what's going on. This is a Poisson random effects model, and we're comparing Mala, random walk, and Barker. And really, if you just look at the bottom 2 trace plots here, these are trace plots telling you about the performance of 2 of the parameters that we're trying to fit. And you can see that Barker seems to be doing a better job of fitting this model than random walk and Mala. So just to conclude, I'm certainly not saying everyone should stop using things like HMC. I'm a huge fan of HMC. But Barker's simple, robust, and efficient, and I think there's a place for it. There's a lot of open questions, and we're currently looking at them. But for now, I think it's just safe to say thanks very much for listening, and I hope you enjoyed the talk. Please see the preprint for more.